In this video, we're going to talk about directory structure. So the first thing we're going to talk about, why do we care? Why do we care how our directory is implemented? Is there a point in changing it around? Should it just be one or the other? So we'll talk about that. We'll talk about trade-offs for design. When we talk about the two most popular ways of doing directory implementation, and that is a linear list and a hash table. So why do we care? So again, we care because the different types of implementation strategies are going to lead to either increased or decreased efficiency, performance, and reliability. And I also want to add in here ease of implementation, ease of coding. I don't know, we'll say ease of coding. That's an important one as well. So some of these are easier than others, and that should be taken into consideration as well. So the first way that you can implement a directory is with a linear list. And so this is just a linear list of all file names with pointers to the block or blocks that they occupy and storage. Okay, so for linear lists, we'll talk about two different ways to implement it, although there are other ways. The first one we'll talk about is an array. Level of difficulty, easy. Arrays are easy. Performance efficiency, kind of bad. So we'll talk about, in some instances, bad, some instances, good. And then reliability, good. So let's break this down. I'm not going to talk about the ease of implementation. You all know arrays. So performance and efficiency, let's think about a couple use cases. So on create, when you're actually creating a file, what would you have to do in an array? So the idea is that you're creating a new file and you want to put it somewhere in your directory or your array. So on create, what you would have to do is you would first have to loop through all of the files to check for the name conflict. So this is going to be big O of n, right? So this is linear. And you have to do that every single time that you want to create. Then you have to insert it into the list. And so arrays have they can do random access. So this can actually, I caught myself here. I'm thinking, wait a second, that doesn't sound right. So they can do random access, but that's not the point. When you have to insert into an array, you actually have to do some intermediate copying back and forth. So it actually ends up being less efficient. You actually end up being linear than actually in constant time. So to insert into a list, you would have to, so here, if you wanted to insert here, you would have to, basically, if you're using a static array, you'd have to reinitialize your array to size +1, and then you'd have to copy this part in, add your new file, and then copy the rest of it in. If you're using dynamic, it's a little bit easier, but you still have to deal with pointers, but it's still the same efficiency. On delete, so again, with an array, you have to search through the list to find the file. So every time you're going to have to search through it. And then to delete an entry, you have a couple options. Some are more efficient than others. You could mark it as unused. So wherever the file that needs to be deleted here, you could just mark it with some, invalid bit to say, okay, I can be overwritten. This is okay. So that's option one. Option two is that you can, if this record is being deleted, then you can take the very last entry in the directory and move it here, essentially resizing it or pushing all of the empty space to the end. It's always easy to trim stuff off the end of arrays than it is to insert inside of them. Or you can delete the whole array and then you can resize it and add it where you want it to go. So those are the three. Obviously, this one is done in constant time. This one can also be done in constant time if you have some helpers. This one is in linear time. Okay. how to solve this. So some things that you can do to make searching and deleting better. You can, instead of for searching, you could sort the list. You could insist that the list is sorted, and then when you need to search, which was whenever we created something or deleted something, we had to search through it, we could use binary search, which is log n, so it's faster than just a linear search. Deleting, we could use a linked list, which leads us to, I think, okay, well, next one, we'll talk about how to implement this with a linked list. But reliability, it's very reliable, so it's there. The array is there, and it's there to stay. And we'll talk about why other implementations are not necessarily like that. Linked list, level of difficulty. My students would probably say medium, maybe some easy, maybe some super hard, but in general, it's not too bad to implement a linked list. The performance and efficiency, some things are really good with linked lists, some things are okay. Reliability, I'm going to mark it as bad, and I'm going to tell you why. Okay, so linked list, you can also use it to implement it. Performance and efficiency, it's going to be easier to add things or remove things from the list in a linked list, especially at the beginning of a linked list. So it's not a huge boost in efficiency here for insert and remove because of our application. We're still going to have to loop through the linked list to find where we want to remove something. Indexing, though, is like way worse in linked lists, right? Because you have to loop through, you have to walk through each one of the links before you can get somewhere. There's no random access. But it does have a little bit of efficiency with the insert and remove also because it doesn't have to use these intermediate data sets or data stores to actually insert remove. So with an array, you have to copy over. If you're not using a dynamic array, you have to copy over the full array into a temporary spot, add something, and then add the rest of the array. So you don't need that with linked lists. You simply disconnect the links. Reliability. So this is the one I said was bad. So reliability. So what happens if the pointer gets corrupted? What happens if this link goes away? Then we lose the rest of our list. So that's not good. And also, so in our linear list of both examples, there's so much searching going on, right? If you want to insert something, if you want to remove something, you first have to check to see if there's a name violation, so on and so forth. So there's so much searching. So we really should have a data structure in place that the searching is super easy to do. Enter hash table. So hash tables they're still going to be stored as a linear list, which you could use an array or a linked list, probably a linked list, which we'll talk about in a second. It could be an array too, but we'll talk about it. But then we use this hashing function to index into. So this is going to make searching a lot easier. Review of hash tables for those of you who haven't seen it yet. So the idea is here. So you have a array or a linked list, and then you have a hash function. This hash function is going to tell you based on some key X where to put your entries. So here I'm going to assume that X is my file name. So this is going to be X. And I'm going to emit the extension. And then the hash function is usually modulo. So you say the ID mod 6, and I have 6 because I have 6 entries here. So I'm guaranteed to put them in one of these 6 spots if I mod it by 6. So the first one mod 6, is going to put it here. So 1.text, right? So 1 divided by 6, the remainder is 1. 6 is going to go here, so 6.text. 28, what? So that's going to be 4 with 4 remaining. So 0, 1, 2, 3, 4. So 28 is going to go here. 33 is going to be 5 with 3 remaining. 0, 1, 2, 3. So 33 will go here. Okay, so it's guaranteed to put every thing in the right place or within these 6 entries. And so this makes it super easy to index into. So if I come in and I say I want file 28.txt, great, I'm going to strip this off and I'm going to use my hash function, and it's going to tell me exactly where to index into. So it makes it really straightforward. Okay, what about name conflicts? So again, we have these files, and let's say, okay, so wait, 1 went here, 6, 28 went there maybe? Yeah, and then 33. So now we have 1.c. It's a different file name because it has a different extension, but it's got the same ID, and it's gonna also wanna come here. So how do we, what do we do here? So typically what's done is this level stays fixed. So this is fixed actually by the hash function. So the number of entries there is fixed. And then what happens here is that this will now become a linked list. So we'll say this top level is an array. We'll just keep it as an array. And then this becomes a linked list of files. So now if I say, okay, I want 1.c, great. So instead of now just indexing in and grabbing this, I'm going to have to walk one more step to grab my actual file, which is still better than if I had to walk through my entire list. So some drawbacks, it's got fixed size because it's tied to the hash function. So if the hash function is mod 6, then it's going to have 6 entries. In this one, size is so it's fixed size. So that's one disadvantage, and then also the reliance on the hash function, which is always the downfall of hash maps and hash tables. So you have to have a good hash function so you have as few collisions, because if you're loading something up so that you're all on one spot in the hash, then you're going to kind of collapse into a linear search anyway, and you lose your efficiency boost. Okay, so again, how to fix it. So you can use what's called a chained overflow hash. Basically it's kind of an extension of this, what I was just saying. You can also use 2 hash functions. If you have a collision, you can hash into a different spot and put it there to do some load balancing. So at this point, let me know if you have any questions, if anything wasn't clear. Thank you.